All right, so last time we ended with the issue of what do you do if clever brute force or your heuristics are still too slow? And we said, well, in that case, change your problem. And for optimization problems, one of the ways to change your problem is instead of looking for the exact optimum, look for something that's approximately optimum. Now, there's a theory of approximation algorithms which actually come with guarantees. For example, an algorithm might output a solution in polynomial time that's guaranteed to be no more than 50% worse than the true optimum. At first, it may not be clear how this is possible. How could an algorithm possibly make that guarantee without actually knowing what the true optimum is? So let me give you a very simple example. The problem we're going to look at here is called minimum vertex cover. The input to this problem is a graph with vertices and edges, and the output is a set of vertices, which we'll call S, such that every edge in the graph touches at least one vertex in S, and such a set S is called a vertex cover. And the goal here is to minimize the number of vertices in the vertex cover. So here's a simple two-approximation algorithm, meaning the output here is no more than a factor of 2 worse than the optimum. Start by picking an edge, any edge. Add both of the endpoints of that edge to S. Then remove all of the neighboring edges. Then pick an edge from what remains, remove all of the neighboring edges, and so on. How do we know that this is a two approximation? Well, certainly by the time we've finished, every edge in the graph certainly touches one of the vertices in S because we only removed edges when we added the corresponding vertex to S. How do we know it's a two approximation? Well, for each of the orange edges that we actually picked, at least one of its two vertices had to be part of any vertex cover because a vertex cover has to touch every edge. So in particular, it has to touch the orange edges. So we know that the S that we picked is no more than a factor of 2 worse than the true optimum, even though we don't actually know the true optimum. So this is often a very powerful paradigm. And here, minimum vertex cover is an NP-complete problem, yet there's a very simple polynomial time two approximation algorithm. However, there are limits to this. Sometimes, even approximation can be hard. For example, we just saw that minimum vertex cover has a polynomial time two approximation. But Denur and Safra in 2005 showed that if minimum vertex cover can be approximated in polynomial time with a factor better than 1.36 ... then in fact P equals NP. So P not equal NP, this question of brute force, can brute force search always be optimized, still stands in the way even of approximation algorithms. And some problems are even worse. For example, the max clique problem, which is given a graph, find the largest clique in the graph, can't even be approximated to within a ratio of n to the 1 minus epsilon, where n is the number of vertices in the graph, and epsilon is any constant greater than 0, unless P equals NP. So before we had a 2 approximation. 2 is obviously independent of the input size. Here, we can't even get, say, a square root n approximation, or an n to the 3/4 approximation, or an n to the 99 over 100 approximation, unless P equals NP. But it's interesting here again, recall that in practice, we can actually solve max clique on a variety of examples using some clever heuristics. There's a very interesting paper by Balcom, Blum, and Gupta in 2009, which show how even when C approximation is hard in this sense, sometimes you can still find an approximation in a slightly different way. So what they showed is, if every C approximate solution, meaning a solution that's within a factor of C of the optimum, actually looks like an optimum solution, meaning not in terms of its value, but in terms of, say, the actual edges it selects or the actual vertices it selects or whatever selection it's making. If it's epsilon close to an actual optimum, meaning in the case of minimum vertex cover, the number of vertices in this solution that differ from the optimum is a fraction of epsilon, then in polynomial time, they can find a solution with order epsilon fraction changes from an optimum solution, even when C approximation implies P equals NP. So sometimes P equals NP stands in the way, and sometimes you can still get around it. But here, note that we're now saying you can find a solution within order epsilon number of changes from an optimum, but we're not guaranteeing anything about how close the value is to the optimum value. In some applications, this may be what you want. Now, just as it's the case that P versus NP doesn't tell the whole story about the difficulty of algorithms in the real world, the same thing is true for these approximation ratios. David Johnson, in his 2010 Knuth Prize lecture, gave this example of the traveling salesperson problem. The problem here is you're given a graph and you have distances on each edge, and the goal is to find a path in the graph that visits each vertex exactly once, where the path is of minimum length. So here you see a list of 5 algorithms that are out there and the corresponding worst case ratio that algorithm gives relative to optimum. So based on this, you would think that the Christofides algorithm might be the best because its worst case ratio is 1.5, whereas all of the others are worse than that. What David Johnson did was test this on random instances of traveling salesperson problem in the plane, meaning you pick random points in the plane, you put an edge between every pair of points, and the distance along that edge is just the distance in the plane. So for example, this might look like this for 10 cities, 100 cities, 1,000 cities, or 10,000 cities. And they were really able to test it up to these sizes, which gives us some confidence that what they're seeing is not an artifact of small input sizes, that they're really seeing some asymptotic behavior. And here's what they found. For the 3 worst case constant factor approximation algorithms, it looks like this. So indeed, the Christofides algorithm, which had a guaranteed approximation ratio of 1.5 worse than the true optimum, beats these algorithms that had a guaranteed worst case ratio of 2. However, when they ran the simple local search algorithms, which had worst case approximation ratios of root n and n to the 1/6, those were even better than the constant factor approximation, even though the theory says very strongly that the opposite should be true. So there's something going on here, and even with approximation algorithms, it's important to test the algorithms on real data to see how they do and not solely rely on the theory to tell you which algorithm is better. So just to recap, when you come across a really hard problem like an NP-complete problem, clever brute force can often be good enough, and you can take advantage of this by trying to reduce your problem to Boolean satisfiability or polynomial equations or integer equations or max clique. When that doesn't work, you can try changing the problem and looking at approximation algorithms. You can combine these by trying to look for heuristic approximation algorithms. But generally, what you're taking advantage of is the fact that your case, the problem you want to solve, is usually not the worst case. So worst case analysis, although it's the focus of much of theory, because it's something that we can get our hands on and we like worst case guarantees, is just the beginning of the story.